So we want to look at lipid metabolism, and you know metabolism would pass anabolism and then catabolism. And then from earlier studies, you know that lipids should be made up of what? We have classes. You have the triglycerols, you have your phospholipids, you have sterols, main classes, but you see sometimes waxes, you have carotenoids, and then even glycolipids. You see sphingolipids too sometimes, glycolipids. But we'll give special attention to triglycerols. We'll treat cholesterol as one of the sterols. But in this particular case, we want to look at fatty acids. Fatty acids. Now, fatty acids can both be obtained from dietary sources. Dietary sources. And then you have de novo synthesis. So that's a synthesis from scratch, endogenous. Now, dietary sources, you have them in the form of triglycerides, and then when they get into the gut, lipases acts on them and then produce what? Fatty acids and glycerols. And then they are compressed again into what? A lipoprotein that is called chylomicron. But we won't be careful not to dive deep into this because we will have them very well later. So you can get what? Fatty acids from what? From diet, and then the body itself can synthesize some should the need be. Okay. Now where does this synthesis occur? You can have them occurring in the synthesis occurring in the liver. You can also have synthesis sometimes occurring in what? Adipocytes. I want to establish the fact that this is what the major hub of what? Synthesis. So the body wants to synthesize fatty acids. It's either occurring in the liver, which is a major point, and then you can also have what? Fatty acid synthesis occurring in adipocytes. Okay. So in producing anything, you have what? A starting molecule. So you need a starting molecule to produce the fatty acid. Now what the body uses is the molecule acetyl-CoA. Now, from what we know, that if we are to enter the pathway TCA, right, we have a reaction that produces acetyl-CoA, which is catalyzed by the pyruvate dehydrogenase complex, right? Yes, that catalyzes the reactions producing acetyl-CoA for us. You can also have acetyl-CoA being produced through beta oxidation of this same fatty acid. But here's the case where we need to produce them, so this is not the case to get a source. We cannot get it from metabolism of glucose through glycolysis. You yield pyruvate, and then this pyruvate dehydrogenase complex is going to act on pyruvate and then produce acetyl-CoA enzyme A. Now, this production of acetyl-CoA is occurring in what? The organelle called mitochondria, right? Mitochondria. But fatty acid biosynthesis itself is occurring in what? The cytoplasm. So how then do we get what? Acetyl-CoA from what? The mitochondrion into what? The cytoplasm to be able to what? To synthesize the fatty acid that what we want. So this is where we mention what we call the citrate shuttle. Now let's consider this. acetyl-CoA itself doesn't have a transporter within the inner membrane of what? The mitochondrium, right? So there's no transporter in the membrane that can take acetyl-CoA out. So then there's a need that we should use a means of getting what the acetyl-CoA into the cytoplasm in this case. Now, what happens is that acetyl-CoA, so this will be occurring in the mitochondria. Acetyl-CoA will react with what? Oxaloacetate. And if you remember very well from TCA, this reaction is catalyzed by what? The citrate synthase. So we are talking about citrate shuttle. Acetyl-CoA doesn't have a transporter, so we have to find a way of bringing it into the cytoplasm, and then we form what? Citrate. So citrate itself has what? A transporter in the inner membrane of what? The mitochondrium. So it can be taken from the mitochondrion and then what? Brought into what? The cytoplasm. So this citrate can be what? Brought into the cytoplasm. So right now you have citrates in the cytoplasm. Citrates in the cytoplasm. Now it is not citrate that we want. It is not a starting molecule. We need to what? Regenerate the acetyl-CoA. So there is a reaction that is catalyzed by the enzyme citrate lyase. Now this enzyme is what? ATP dependent. The enzyme is ATP dependent. What happens is that the enzyme is going to cleave acetyl units. Cleave acetyl units from citrate, and then what? There is coenzyme A, a pool of coenzyme A within what? The cytoplasm already, and then it adds the coenzyme A to what? To the acetyl unit, and then it will give us acetyl-CoA. This is what we wanted, right? Now, after getting acetyl-CoA, you remember the reaction that occurred here, oxaloacetate was produced. So after getting acetyl-CoA, also what? Generates oxaloacetate. Now, we have to realize at this point that there is a molecular imbalance. The body has used oxaloacetate, pushed it from the compartment of the mitochondrion into what? The cytosol. You need to compensate for what? That imbalance. So that means that we should find a way of what? Sending oxaloacetate into the mitochondrion. Now, note that oxaloacetate doesn't have a transporter that can get it into what? The mitochondrion. So what happened in the cytoplasm is that the enzyme malate dehydrogenase will now act on this oxaloacetate and what? So to convert oxaloacetate to what? L-malate. Now, malate has what? A transporter within the inner membrane of what? The mitochondrion. So it cannot enter the mitochondrion. And that transporter is called the malate. The malate what? Alpha ketoglutarate. Alpha ketoglutarate what? Transporter. Alpha ketoglutarate transporter. Now, when this malate gets into the mitochondrion, then the same enzyme, malate dehydrogenase, let me change my marker. The same malate dehydrogenase will act on what? Malate and then generate what? Oxaloacetate. So that means that what? We have balanced what? The molecules. We've got what it took from the mitochondrion back to it. But oftentimes, this system of transport doesn't happen, because as soon as you form malate in the cytoplasm, there is an enzyme that is within the cytoplasm that acts on it to produce what? The reducing equivalent NADP And the enzyme is called what? Malic enzyme. Malic enzyme. Now, this malic enzyme, what it does is that it catalyzes oxidative decarboxylation. Oxidative decarboxylation. So decarboxylation, and that is going to remove what? CO2. So you have your L-malate plus NADPH. NAD plus, because we are now coming to see the reducing. It is going to give you CO2, right? And then yield NADPH, and then the molecule was pyruvate. So malic enzyme will act on L-malate and then take hydrogen, reducing equivalent, give it to NAD plus to form NADPH, and then take away CO2 and then give you what? Pyruvate. You know this is what? A 4-carbon compound, and then pyruvate is what? 3 carbon. So after CO2, 1 carbon is taken out, then you get pyruvate. Now, because we said that this process that we talk about here doesn't often occur, so we've not balanced molecules, we've not got oxaloacetate back to the mitochondria. So what happened is that there is a transporter for pyruvate in the membrane of the mitochondrion. So it takes pyruvate into the mitochondrion, and then an enzyme called pyruvate carboxylase. Pyruvate carboxylase will act on pyruvate and convert it directly towards oxaloacetate. And in that sense, we have what? Molecular balance again, and it will form what? Pyruvate for us. And this enzyme is what? ATP dependent. So what we're trying to say is that, well, the malate could be transported, but it is not what? A normal reaction. As in, it doesn't happen often, because as soon as you have malate within the cytosol, malic enzyme directly what? Acts on the malate, and then what? Through oxidative decarboxylation, it will form what? NADPH, give out CO2, and then what? Form pyruvate. Then this pyruvate will be taken in by what? A pyruvate transporter into the mitochondria. Then this ATP dependent enzyme, pyruvate carboxylase, will now form oxaloacetate. And carboxylase is going to add what? CO2 to pyruvate, which is 3 carbon to form what? A 4 carbon compound. So that is the cyclic shuttle. Now you see that with the processes, 2 ATP salts were involved. The one for what? Cyclic lyase, and then the one for what? Pyruvate what? Carboxylase. So that's how the body gets acetyl-CoA into the cytoplasm from the mitochondrion for the synthesis of what? Fatty acid to begin. Okay. So now let's look at something. Now you now have acetyl-CoA in the cytoplasm, right? You have your acetyl-CoA has been brought. Now what's happening is that there is a reaction that is going to what? Take place, and that reaction is for the formation of another compound called what? Malonyl-CoA. Now this is 2 carbons, and this is what? 3 what? Carbons. Now there is an enzyme here called the acetyl-CoA carboxylase. Acetyl-CoA carboxylase, ACC for short. It has 2 functions. It has what? A biotin carboxylase function, and then a carboxyl transferase function. So we are looking at the enzyme. It has a prosthetic, that's biotin, right? That's biotin, B7, vitamin B7. And also has the metal cation, Mg2 plus or what? Mn2 plus, so you must see any of them in the books or slides that you'll be reading. The metal cations are mostly to stabilize what? The enzyme through what? Charge compensation. Okay, so it has these two functions, right? And it's going to catalyze the formation of malonyl-CoA from what? Acetyl-CoA. Now, let's look at this. Acetyl-CoA will be given what? A carboxyl group by a bicarbonate, right? To form what? Malonyl-CoA. To be given carboxyl groups, C-O-O-. Now, we said that ACC has a biotin carboxylase what? Function. So it is the biotin, the prosthetic group that is going to receive what? The carboxyl group first. And then there will be an intermediate form. And then the carboxyl transferase what? Function will take the carboxyl group from the biotin and send it to what? Acetyl-CoA, so that will form what? Malonyl-CoA. So this carboxyl group is coming from what? Bicarbonate. It first picked up by biotin. So we have the biotin carboxylase function of the enzyme to give the carboxyl group to biotin, forming an intermediate. Then afterwards, the carboxyl transferase function what? Will take the carboxyl group from biotin, the intermediate, and then what? Send it to acetyl-coenzyme A to form what? Malonyl-CoA. Note that this enzyme it functions in its polymeric form, and later on when we are looking at, so it functions in its polymeric form. So later on when we are looking at the regulation of fatty acid biosynthesis, you see that citrate what? Upregulates this enzyme. How does it do it? It what? Stabilizes the polymeric conformation. So if this acetyl-CoA carboxylase should function, it should be in what? Its polymeric form. And then citrate what? Stabilizes this polymeric form. It is the citrate works as an allosteric what? Activator. The citrate stabilizes what? The polymeric conformation of what? The enzyme, so that we form what? We form malonyl-CoA from what? Acetyl-CoA and what? Bicarbonate. Now, okay, so we need to note that the NADPH, right, that is mainly used during the synthesis of fatty acids are mainly produced by what? Malic enzyme. We have looked at that process already, so no need going into details. And then another source is from what? The pentose phosphate pathway. It also gives us what? NADPH. But mostly the ones that are utilized in what? The synthesis is what? From malic enzyme, and then we get what? A lesser amount from what? NAD. So this is how acetyl-CoA what? Enters the cytosol, and this is how what? We form the two the starting molecule, right? So malonyl-CoA and then acetyl-CoA at this point will now initiate what? The process. Okay. So that's it. We'll look at the synthesis in the next video. Thank you very much.